So now we're going to switch topics in this course. Well, the things we're going to talk about are related to this topic of random covariance matrices, as we're going to see later. But right now I want to define a problem and begin its study without any reference to randomness. So it's just a different kind of problem, right? And the general field, the general heading for the subject is compressed sensing. And let me start with a kind of motivation before which in some sense is the original motivation for the subject before I start doing the mathematics. So apparently the modern theory of compressed sensing started out with a very applied problem. And I mean, this is described, there's a paper which is in the lecture notes, by Manuel Candés. He gave a talk in ICM 2014, you know, where they give the Fields Medal. His talk was called Mathematics of Sparsity and a few other things. And what I'm going to try to do here for a little bit is to try to reconstruct what his original motivation for this whole research topic is. So as I said, it started out with a very applied problem. The problem is this: one of the techniques you have for figuring out if there's something wrong in someone's head is to do a magnetic resonance exam. So what you do is you have the person lay down on a kind of hospital bed. Okay, you can tell I'm not a very good drawer, right? And then you have this huge machine that comes over, right? And sends magnetic pulses that travel through the person's skull and through all the person's tissues, right? And you need to do this usually for 10 minutes. And then in the end, what you get is you have some sort of vector, which should really be a function, but once you discretize, it's a vector. And this vector, well, for time being, it's just going to be beta, a vector in a very large dimensional space. And the measurements you get are just some values xi, which correspond to the inner product of this vector with the pulses in some sense. I mean, I'm not being very clear about this. In some sense, what the pulses tell you are the frequencies of this signal here. Okay. And the goal somehow, so you have the pulses here. And the goal is you want to reconstruct beta from the pulses. So you know what the xi's are, you know what the yi's are, you don't know what beta is, and you want to reconstruct it from knowledge of the y's and the x's. And what you want, of course, to have as few pulses as possible. So in one situation where this comes up, I mean, there's two reasons for having as few pulses as possible. First of all, it makes the problem simpler to solve. I mean, this is a very high-dimensional problem. So the smaller the number of pulses is, the smaller is the linear system you need to solve in order to recover beta. And there's another reason, which is, as I said, usually MRI, magnetic resonance imaging exams, they take on the order of 10 minutes. But if this patient happens to be a child, then it's very hard to keep a child still for 10 minutes. So essentially, the classical way out of this problem is just to make the child fall asleep by giving it some sort of tranquilizer, which is a dangerous thing to do to a child. So people usually avoid doing that. Right? So you want a way to use very few pulses, a number of pulses they can get in a limited amount of time, and yet be able to recover this beta here. Right, so in mathematical terms, let's write this matrix A where the rows are given by the vectors x's. So it's a matrix that belongs to n times p, right? So you have n pulses, and each pulse is p-dimensional because the signal is p-dimensional. And you have this vector y, which is a vector of all the measurement results. So you have all, which belongs to Rn. So you have A and Y known. And you want to solve a beta, and I'm just going to say beta min. I mean, there's a reason for the beta min, which I'm not even sure I'll get to. But you want to find this vector here, which is sort of the true thing that you worry about. Right? But of course, I mean, so in general, if I want to solve this problem exactly, how large do I need n to be? Okay, let's see, right? So this is a system of linear equations. So I have the number of equations is n. The number of unknowns is p, right? This is the dimension of the vector b. So in principle, you should ask for n larger than p, right? So, or at least equal to p, right? So we want this matrix A to be invertible here. And it's clear that for general beta, you can't do much better, right? So if n is less than p, and then there exists two vectors b2 such that A times b1 equals A times b2, and this means that you can't recover the vector beta 1 from the values of the measurements because it has the same values as beta 2. Right, this just stems from the fact that you have a linear map from Rp to Rn. If p is greater than n, then the kernel of this map is non-trivial. Right. So, and that would be the end of the story, of course, except that in many applications, you have vectors beta that are sparse or approximately sparse. So let me define this thing, which people really abuse this notation here. So whenever I write the zero norm here, it's not really a norm. It's just the number of coordinates of the vector that are non-zero. And what I mean here by sparse, I just mean that either the number of non-zero coordinates of beta min is much less than the ambient dimension, or you can approximate it very well by a vector that's sparse. Maybe your vector beta min has 3 coordinates that are very large, and all the other ones are tiny. You add them up, and the effect is minor. So in that case, we'd say that beta min is approximately sparse. Right, so sparse is really the key word here. And I mean, is it true that, for instance, in this application of MRI, the vectors are sparse? Well, not quite. So I mean, in this case here, what you're talking about is really is not just a signal, one-dimensional signal, but it's a two-dimensional image. But what you can say is that if you look at neighboring pixels in your image, it tends to be the case that two neighboring pixels have very similar colors or very similar gray levels. And actually, most of the time, maybe they're exactly the same, up to a certain small error. Which means that this vector is not that it's exactly sparse, but has sparse gradients in some sense. So the increments, if you look at this vector that describes the increments from one pixel to a neighboring pixel, then this vector is very sparse. So there is a basis in which this vector beta min is parsed. Right? Well, in other cases, maybe you have something that's more like a signal, right? Which is you have a continuous signal, say a sound signal. And then you discretize in order to get a vector beta. Is it reasonable to assume that this vector is sparse? Well, not in the usual basis, right? Not if you say, I want to look at the basis where given by these points here. Here the function might take many different values, and the values are typically not going to be 0. But we know we can do something, which is to switch to the frequency spectrum. Take the Fourier transform of this signal here. And when you do the Fourier transform, typically what you have, well, I mean, depends on what kind of application you're talking about, right? But typically what you have is you have the low frequencies matter a lot, and then the high frequencies are sort of negligible. So this is more or less like saying your signal is sparse in the sense that you can ignore everything that comes from here. So up to a certain approximation, you have a sparse signal. In any way, I mean, the mathematical problem, I think, is very well defined, right? So you're just saying, I want to solve a linear system of this form under the assumption that beta min is sparse, that has a number of non-zero coordinates that's much less than the ambient dimension, right? Well, I mean, there are other settings where this comes up. Sometimes you have settings where you might say that your measurement is an inner product plus a noise term, which you can think is a Gaussian random variable, for instance. And there are many settings where this is useful, which are very different from this. For instance, when you do, I mean, there's a very famous example, which is about prostate cancer. You have many patients, and each patient's a huge vector describing the patient's age, height, weight, and many other indicators at different points in time, perhaps. And then Y would be, well, all those patients undergo the same treatment for prostate cancer, and Y is the number of years they live after the treatment's finished. Right? And then what you expect, so this thing here would describe how a typical patient reacts to the prostate cancer treatment as a function of its characteristics. So you assume the response to the treatment is linear, and sometimes it's reasonable to assume that it's also sparse, meaning that of all these thousands of measurements you have of a single person, maybe only 3 or 4 of them matter in terms of determining how long that person is going to survive. Right? So, I mean, there are many examples. I'm really not going to get into any of them. I mean, Condé's paper has more examples. It has examples related to sparse matrices as well. But anyway, so the mathematical problem is very simple. Or at least the version of it that we're going to study. So you have your system, and now min. And can you recover beta min from, or maybe I should say, when can you recover beta min from Y in the matrix A? And you assume, and this is all going to become clear later on, but you assume that you have a sparse vector, so the number of non-zero coordinates is less than P in some sense. And I should say right away that in the way I pose the problem, the answer is actually yes. I mean, it's not that for any matrix A, this is a good problem. We're going to see that in some sense for a generic matrix A, that you can recover the vector beta min. Right? I mean, this is not going to be the end of the story, but I'm just going to say that this is a well-posed mathematical problem in some sense. And let's consider this let's say this. So definition say that A is generic if any p columns, let's say you have n rows in p column. Now any, okay, let's see, any n columns of A are linearly independent. It should be clear that this property is generic in the following sense. So when you take n columns of A, you have n rows and n columns, right? So you have a square matrix. And the set of square matrices that are invertible and therefore have linearly independent columns is an open-ended set in the space of all matrices. Right? Or you can say, well, suppose that the entries of matrix A are random variables which have a density with respect to Lebesgue measure. And then you can show that the probability of A being generic is 1. That's very simple to prove. Right? So generic matrices are generic in the sense that they correspond to the set of non-generic matrices is a set of 0 Lebesgue measure in this NP-dimensional space, and also the set of generic matrices is open and dense. So if you have a matrix that's not generic, you can perturb it a little bit and get a generic matrix. If you have a generic matrix, even perturbing it a little bit will still keep it generic. So now okay, so let's say I'm going to define a problem here, which I'm going to call P0, which is an optimization problem. So I'm going to minimize the norm 0b subject to beta belonging to Rp, and A times beta equals y. So here I have a system of equations, right? The same system as before. And what this problem is asking you is to find the solution to this system. Of course, there are infinitely many in principle, right? Because you're just saying that, well, the number of equations is less than the number of unknowns in principle. So this is telling you that there are infinitely many solutions, but I'm not asking you to find one of those solutions. I'm asking you to find the solution which is the sparsest, with the least possible number of non-zero coordinates. Right? Remember, this is just a number of non-zero coordinates of vector beta. So of all solutions to the system, we know there's at least one, right? So because of this. Find me the one with the least number of non-zero coordinates. And here's the theorem. If, so remember that y equals A times beta min. If A is generic and beta min has at most n over 2 non-zero coordinates, then, sorry, there's no tilde here. Then beta min is the unique solution to P0. Let's see if you understand what I mean by this. So I'm saying, so I have two conditions here. One, I need A to be generic. The second condition is that the vector beta min, it has a number of non-zero coordinates which is less than n over 2. Less than or equal to n over 2. So I'm not claiming here that I can solve this system when, say, the number of non-zero coordinates of beta min is p, right? So remember that we want to consider the case where the number of equations is less than the number of unknowns. Otherwise, everything's sort of trivial. So we're in this regime. So we cannot expect to solve a general system of equations, right, with n equations and p unknowns. But we can expect that if we know that there is a solution which has at most n over 2 non-zero coordinates, then we can recover it by this problem. It's going to be the unique sparsest solution to the system. And the proof is really simple. So you take beta hat, a solution, some solution, to P0. And I'm going to define delta hat as the difference between beta min. Right? And I'm going to claim that, so clearly you have the alpha A times delta hat equals 0. Just because it's a linear system, right? Because delta hat equals alpha times beta hat minus A times delta hat equals A times beta hat minus A times beta min. And by assumption, right, you have those two are solutions to the same system, so we have 0. I'm using the fact that A is a linear transformation, so I can write this down. So now I claim so I have this thing here. I'm just going to call this 1. Note that number 2, that the number of non-zero coordinates of delta is n at most. And why is that? Because beta min has at most n over 2 non-zero coordinates. And I claim that the same is true about beta hat. Why is that? And necessarily we have the beta hat, the L0 norm of beta hat is less than the L0 norm of beta min. Why do I have this? Well, how did we define beta hat? It's a solution to this problem, right? So you take all vectors that satisfy these two constraints and look for the one with the smallest L0 norm. And you can notice that the beta min satisfies this. Right? So we don't know what beta hat is, but we know that its L0 norm is at most the L0 norm of beta min. And now what we have is that delta, well, what's the number of non-zero coordinates of delta? Delta hat. Well, if you have a coordinate of delta that's non-zero, it must be the case that the corresponding coordinate of beta min is non-zero, or the corresponding coordinate of beta hat is non-zero. Right? So, so I claim that in general, you have this property here. If you take the L0 norm, or the number of non-zero coordinates of a sum of vectors or a difference, this is less than the number of non-zero coordinates, the sum of the number of non-zero coordinates. Right? So, right? So we're in good shape here. So we have this property number 1, we have property number 2. And I claim that these two together, they imply that delta hat is equal to 0. Well, let's say that A1 equals AP denotes the columns of A, right? So we know that when you take A times delta, the result is a linear combination of those vectors, right? So it means that A times delta hat is a sum from I equals 1 to P of delta hat I, AI. But actually, I mean, you don't need to sum over all indices, right? We know that only a few of these guys are non-zero. So this is the same as a sum over over coordinates such that delta hat I is different from 0. So this sum has, well, as we just saw, it has at most n non-zero elements. Right? Just saw that the number of coordinates is less than n. The number of non-zero coordinates is less than n, or less than or equal to n. But I mean, you also know that this is 0, right? This is property number 1. And this is another way of writing property number 2 over here. So I have a linear combination of vectors which adds up to 0. And I know that the sum is a linear combination of at most n vectors. Right? So there's this a linear combination of less than n columns with sum 0. Now I use the fact that A is generic, right? We know that any n columns are linearly independent. It means that if you want this to be true, we've proven that this is true. This can only be true if these coefficients are all 0. So, and from all of this we deduce that delta hat E equals 0 for all I, which means that delta equals 0, which means that beta hat equals beta min. So, I mean, and maybe let's just go back a little bit. So I've used a few things here. So, I mean, the general idea of the proof, which is going to come up later, as we're going to see, this is not really the ideal way to recover a vector beta min, and I'm going to say why in a second. But the general idea is actually going to be used, right? So you have the vector you want to recover. You have an algorithm that gives you some other vector, which is potentially different. And maybe it's not even uniquely defined, right? Who said that this system doesn't have infinitely many solutions? Well, what you can prove is this. So you can prove that this difference, well, it's a vector in the kernel of the matrix A. And it's also a vector that has some defining characteristic here. In this case, the characteristic is that this vector has at most n non-zero coordinates. And then you say, well, the kernel of this matrix, so this part of the argument says, the kernel of A does not contain any vector with n or less non-zero coordinates except for the 0 vector. So maybe I can put it like the key step here. Well, the condition that A is generic implies this, so that actually it's equivalent to for all that the kernel of A intersection, the set of n sparse vectors, this intersection only contains the 0 vector. Right? This is the last part of the argument. I said, take a vector that's in the kernel and has at most n non-zero coordinates. The same argument we showed here, right? Our argument here was, well, we have this vector in the kernel of A, so A times the vector is a linear combination of at most n columns, and because the n columns are linearly independent, that means that this vector here is 0. So this is what we did. Right? So this is how being generic is useful for us. But now I want to argue that this is not really the thing we want to prove. I mean, we have a well-defined problem. It's good that we have this because we know now that this problem here, this mathematical problem, is not hopeless. Actually, you have a solution, right? There's a way to recover a sparse vector from a system of linear equations that's underdetermined as long as the sparsity level of the vector is less than half of the number of equations. Okay, that's very good, but this is not really a very good method. And the reason for this is that, well, then you can think, well, how am I going to implement this in a computer, right? What do I tell a computer in order to try to figure this out? How do I solve this problem in a computer? Let me tell you what the obvious method is. Right? So, first of all, you check whether 0 is a solution to this linear system of equations. Right? If it is, then you're done. You've found the sparsest solution. Then you try to find all solutions that have at most one non-zero coordinate. So those are the multiples of one canonical basis vector, or canonical basis vector E1, and then multiples of E2, and multiples of E3, and so forth. So you try all of the P possibilities that you have. And if one of them is good, then you know you've found the sparsest solution, right? Otherwise, you would have stopped before. Then you find that if that doesn't work, you try to find all vectors that are in the span of two canonical basis vectors, which might be solutions of this. So you try the first two coordinates, E1 and E2, E1 and E3, E2 and E3, E3 and E4, and all possible combinations. And you try to find whether there is a solution of this kind. And you keep going, right? At some point, maybe you try, okay, I've tried to find solutions that are a combination of at most 99 basis vectors. So now, since I haven't found any, I know that the sparsest solution has 100 or more non-zero coordinates. So I'm going to try all subsets of size 100 of the canonical basis vectors, and maybe one of them will give me a solution. If no set doesn't give me a solution, then I'm going to move to 101 canonical basis vectors, and then to 102, and then to 2 million until I find a solution. And you can see what the problem of this idea is, right? It's computationally very expensive. You might end up trying all subsets, even if you know that there's an upper bound, right? You're going to stop at n over 2. But let's say that P equals 10 million, which is really not too far-fetched. Let's say that P equals 10 million, and then N equals 1,000. So do you really want to try all possible subsets of size 1,000 of a set with 1 million elements? I mean, that's going to take forever, right? You're sort of fighting against combinatorics when you do this. And it's always bad to fight against combinatorics. So, and then there's a question of whether there's a better method, right? So I started describing this combinatorial method where you just try all possible combinations of basis vectors. I started by describing it as a kind of an obvious method. It's a stupid method, perhaps. Maybe there's something better to be done. But in general, at least, we know that solving this kind of problem is NP hard. And I'm not going to get into what that means. But it means essentially that if, well, among other things, it means that if you find a polynomial time algorithm for doing this, for any vector, for any matrix A and any vector Y, then you can win $1 million by proving that P equals NP, and you'll be very happy. And, you know. But that's probably not going to happen. Probably P is different from NP, and there's no way of solving a general system of this kind. I mean, you could keep going, right? You could say, well, are there any assumptions on the matrix A that allow me to solve this problem efficiently? And that's an entirely different matter. What we're going to see instead is that there is a different way to modify this problem so that you always can find solutions efficiently. Right? And it turns out that, well, we're going to modify the problem, as I said. So when you modify a problem, there's no guarantee that the solutions stay the same. Right? But it turns out that for most choices of matrix A, and most means in some sense in probability, you can prove that the other problem has the same solution as this one. So what is this modification, right? So here we had a property of A that guaranteed that this problem had a unique solution, which was exactly the vector it tried to find. So, so let me first modify the problem, and then we'll see what we can do. So, well, I need a new definition here, which I guess so problem is going to be called P1 now. Let me just say that the L1 vector, the L1 norm, sorry, of a vector is just the sum of the absolute values of the coordinates. It's just L1, right? So you replace the usual round ball by something like this. My new problem is the problem of finding, again, I look at vectors that are a solution to my linear system. But now instead of looking for the sparsest vector that is a solution, I look for the solution with the minimal L1 norm. I mean, there's a name for this, which is, well, Dave Donahoe was one of the inventors of this subject, calls this basis pursuit, which in some sense means that you're trying to find the right basis, meaning the right basis vectors, because you want to find a sparse vector that's more or less equivalent to finding which vectors in the canonical basis I want to use to express beta min. Okay. So, so this is a problem, and we're going to show that under certain conditions on A, that this problem has the same solution. I mean, a theorem very similar to this one. If A is good in some sense, and beta min sparse, then the unique solution to this problem is exactly beta min. Right? Right. So, I mean, the first thing we want to understand is that what replaces this remark here. Right? In the end, I mean, the first version of this result, right, in the L0 algorithm, the fact that A was generic told us that there's no sparse vectors in the kernel of A other than the 0 vector. And how did these sparse vectors show up? Well, the sparse vector showed up because I took a solution to the problem P0. I subtracted the solution I wanted to get, P min, beta min, and I argued that that was a sparse vector, a vector with less than n, at most n non-zero coordinates. Right? So the first thing we're going to do here is to try to understand if, I mean, here, so the crucial thing here was to be able to say that, you know, the difference between the solution and the solution of the problem and the vector I wanted to find must be a sparse vector. And then you have to argue that the kernel doesn't contain sparse vectors outside of 0. And now we're going to try to figure out what if we have a similar property here. And that will tell us what A should satisfy in order for us to be able to prove that this problem is good. Okay, so what do I mean? I'm going to prove now a lemma. So for the time being, I'm not going to try to argue that the solution, the unique solution to this problem is exactly beta min. I'm just going to try to say something different. So definition, you take a subset of the coordinates, which is non-empty, right? You take a number kappa greater than 0, and you define this constraint set. I mean, sometimes people call this the cone, but it's not, well, it's not a cone. So where is it? Well, it's sort of like a cone, but anyway. This set of vectors, just take the set of all vectors such that when you sum the absolute values of the coordinates outside of S, the sum is at most kappa times the sum of the coordinates inside S. Why am I defining this? Well, it will become clear soon. But let me argue. I'm just going to give you a very brief reason why this is a set of vectors that are sort of like sparse vectors. And since we cared about sparse vectors, this set should matter to us. Well, so in general, so let's see. I mean, this is one of those exercises that we all do at some point in life, right? So in general, you can look at the ratio of the L1 norm to the L2 norm for p-dimensional vectors. So how large can this be? If I tell you this, I have a vector in 10 dimensions with L2 norm equal to 1, so Euclidean norm equal to 1. What's the largest possible L1 norm for this vector? Upper bound. And then we can prove the lower bound. Right, so I mean, there is a upper bound for this which comes from Cauchy-Schwarz, right? You look at this. So here you have an inner product of some sort. So you can say, well, this is less than 1/2 times the sum of 1/2. So this is going to be square root of p, right? So in general, this inequality here is best possible. Now, if x is S sparse, meaning it has S non-zero coordinates, then you have a better inequality. Or if this is less than p, right? Then you have a better inequality, which is we apply Cauchy-Schwarz, but you notice that you only need to consider S coordinates. So this tells you that this inequality here is best possible. Right? Now, what about vectors in this set here? This is actually a lemma in the notes that we're going to use later. Well, what's the L1 norm of a vector here? It's, it's the sum over all I of norm of xi. But you can split the sum into a sum of guys that do not belong to S and a sum of guys that do belong to S. And this, by the definition of the set, we know that the first term there, the first sum, is less than kappa times the second. And now you can apply this Cauchy-Schwarz thing and see that this is less than kappa plus 1, square root of, okay, the size of S. Now let me just say that little s is the size of S here. And you get here sum I belonging to S xi squared, 1/2. And this is at most the norm of x, right? You're just taking kind of the norm of the projection of x onto the coordinates in S, but this is less than the norm of x. The L2 norm, I mean. So you notice that if a vector is general, then the ratio between L1 and L2 is essentially the square root of the dimension, in the worst case. If the vector is sparse, then the ratio is square root of S. If the vector is in this set that we just defined, then the ratio between L1 and L2 is sort of the same as if the vector was sparse, which essentially means that in some sense that most of the important information about this vector is in the sparse part, the subset S. Well, I mean, that's not quite precise. But in any case, I mean, this sort of tells you, I mean, if you look at a kind of a generic vector, for instance, if you take a random vector in the unit sphere and you compute its expected L1 norm, then you can see that it's not going to be very different from this. So this is telling you that vectors in the set are very non-generic, and I don't want to make this intuition very precise because it isn't very precise, but in some sense, vectors in this set turn out to be sort of like sparse vectors. And here's the result we want to prove about this set. So which is the following. So take, it's a proposition. Take beta as a sum solution to the problem P1. And then, okay, let S denote the support of beta min, which is just the set of the set of coordinates of beta min that are non-zero. Then the difference between these two vectors belongs to CS1. So the set of coordinates S is going to contain, you could say it contains at least half of the L1 norm of the difference. Right, so why is this true? The idea is similar to what we showed before, right? So we have that, okay, I'm going to use this part of the board here to prove this. It's an Arab style proof where you write from right to left, right? So here's the proof. The proof is simple, but it's good to, it's not entirely obvious, right? So, okay, the proof is, well, we know that alpha beta equals y, which equals alpha beta min, right? Well, I mean, I should have said this before, right? But it's not entirely clear that there is some solution to the system, except that we know, right? From the beginning, we're assuming the system has a solution. Right? So it's important to notice that at some point. Right? And so beta has minimal L1 norm, right? Meaning it has minimal L1 norm amongst all solutions to the system. What this implies then is that the L1 norm of beta hat is less than or equal to the L1 norm of beta min. And let's write this in terms of coordinates, right? So you have, and let me write it like this. So take the sum over coordinates in S, say S complement, the sum over coordinates beta hat I. S, remember, S is a set of non-zero coordinates of B, or beta min. Right? So what I'm saying, the sum of these two things is the L1 norm of beta hat. The L1 norm of beta min is actually just one sum, right? Because all the non-zero coordinates of beta min are in S. Well, by definition of S. Right? Here we're using the fact that that if you take a coordinate outside of S, then beta min, if you take an index outside of S, the corresponding coordinate of beta min is 0. Now I'm going to move these things around. So I'm going to notice that I left a gap here, and that's for a reason. Right? I just moved this sum to the other side. Now I want to change this a little bit. And I want to change in two ways. Well, first of all, I'm going to notice that because of this thing, I can add beta min here. It doesn't change anything. This is 0. On the other hand, if I just want an upper bound, I can use a triangle inequality and erase these things here. What do I have here now? Well, this is the ith coordinate of delta hat. This is for I belonging to S complement. And this is the ith coordinate of delta I for I belonging to S. So what I proved is that the L1 norm of delta hat restricted to S complement is less than the L1 norm restricted to S, which is precisely saying that delta hat belongs to CS1. So this proof's a bit subtle, but it's a very nice argument, right? That well, you move this and you get the sum of delta i's for I in S, and on the other side you already have the sum of delta i's for I not in S. Right, so now we know something about right, which is sort of analogous to what we knew before. Remember, in the previous problem, what we knew about delta hat is that it had to be a sparse vector. It had to be a vector whose number of non-zero coordinates was at most twice the number of non-zero coordinates of beta, or beta min. Or meaning, because we assumed that the number of non-zero coordinates of beta min was less than n over 2, or at most n over 2, the number of non-zero coordinates of delta had to be at most n. And then we said, well, then we needed some sort of a condition here to make things work. Right, so what about this? So now we can sort of start to think about what we need in order to finish this argument. Right, so what do we need the matrix? So in the end, we want to prove a theorem that says if beta is sparse, meaning the number of non-zero coordinates is less than blah, then this problem has a unique solution, which is beta min. That's what we want in the end. So here's a sufficient condition on A. Right? So before we had this. So what we want now, so let me, I mean, in some sense it's necessary and sufficient, but I just want to say that it's sufficient. In the previous case, also this condition of A being generic, so it's necessary and sufficient. But let me say that the sufficient condition would be this, that the kernel of A, its intersection with this restricted set, only contains the zero vector. So suppose we know this. Then we can come over here and say, well, if I have some solution to problem P1, this delta hat belongs to the kernel of A, right, by the same argument as before. Right, because I have two solutions to the same system, so their difference is the kernel. So I know that it's in the kernel. I know that it's in the constraint set. So if I know that the intersection of the kernel and the constraint set only has the 0 vector, then that shows that beta hat equals beta min. Shows that delta hat is equal to 0. Right? So the question is, you can say, put it like this, or how generic is this? So before we had a very clean theorem that said, for instance, the set of matrices A that are not generic is a set of 0 Lebesgue measure. And yes? Now, before we said, well, we had this concept of a generic matrix, meaning that any n columns were linearly independent. And we said, well, the set of such matrices, the set of matrices that are not generic is a set of 0 measure under Lebesgue measure. So if you take any probability measure, say, on matrices that's absolutely continuous with respect to Lebesgue, the probability of having a non-generic matrix is 0. And even if you take a distribution that's, say, discrete, because that's sometimes more convenient, you can usually prove that that happens only with a very small probability. I mean, you can actually get bounds on that. No, it's not very hard. And the question now is, can we hope that this is equally generic? Okay? In the sense that, can we hope that, that a typical matrix A from some probability distribution will satisfy this? Well, the answer is yes and no. We can hope, but the probability is not going to be exactly 1. It's just going to be very close to 1. So it's going to be like one of those probabilities that I showed before. It goes to 0 exponentially fast. The probability of not being generic, not satisfying this, is going to go to 0 very fast with some parameter. And they're going to see next class that how we can prove this using the things we already know about random covariance-type matrices. But before we move on, let me just say that, well, we're actually going to prove something which is slightly stronger and which is going to look like, so just give you a rough plan for tomorrow's lecture. Right, so we want to prove that for certain kinds of A, this is satisfied. Okay, so the first part of the plan is an even stronger condition. Which is to show that for all x in this constraint set, if you look at the norm of A times x squared, say, this is larger than, say, norm of x squared over 2. Actually, norm could be norm of x squared times any positive constant. Right, this certainly implies this. Right? Because, well, if you know this, then you take a non-zero vector in here. It cannot be in the kernel of A, right? Norm of A times x is going to be larger than the norm of x, which is positive. So there's an even stronger condition. And it turns out that you need this sort of stronger condition in other problems, in more kind of statistical problems where you remember that we're assuming that you have this exact relationship here. If you add noise to this, then you need a stronger condition like this. So this is the kind of condition we want to prove, and we want to prove it for random matrices A of a certain kind that I'm not going to describe. So you can actually try to think how you could prove this. And I guess that by now the idea should be that somehow we can rewrite this as x inner product A transpose A, x is larger than 1/2 whenever x belongs to C S1 and the norm of x is 1. So it's some condition. And you can hope that maybe you can use one of those epsilon net methods to try and do this. Right? Maybe you want to prove something even stronger, say that this is between, say, 3/2 and 1/2. Or even, which would be something similar to saying that A transpose A minus the identity has something like a norm that's less than 1/2, except that you only measure the norm by using vectors in this set. I'm not being very precise here, right? So there's some concept of norm. What's the norm of a matrix? It's just the maximum of this x in the product matrix X when X has norm 1 and belongs to this set. You could try to do something like this and find an epsilon net and prove from there. But it turns out that's not completely straightforward. Kind of the trivial epsilon net argument doesn't work so well here. Well, there's actually a paper written on this by Mark Rudelson and Shuzheng Zhao, where they show that they use some sort of epsilon net argument to prove this. In the following sense, actually. Let me be a bit more precise. Okay, so what I want to say, what we're going to prove is some sort of statement like this one. And what they show is that if it's something like this. So if you have that A times x squared is less than 3/2 x squared and more than 1/2 x squared for whenever the L0 norm is less than 10 times the size of S, then you get this condition here. And so, let me say why this is a nice result. This, as I said, you might try to build an epsilon net argument for this kind of thing, but it's not going to work very well. It's very hard to find an epsilon net for this set. Remember that before we needed epsilon nets for the sphere, and the sphere is very easy to understand. This is not as easy. But what the Rudelson and Zhao showed is that if you can prove this sort of inequality for all sparse vectors, then it follows that you have this. But, and what we're going to see is another argument, which I showed it's in my, I hate to cite myself, but I'm going to do it again. So there's another argument of this sort, which is actually weaker. And the difference between the two arguments is, there's two differences. That you need weaker conditions, and the proof is about 1/10. The length of the proof is about 1/10 of the length of the other proof. So it's going to see it's very simple. And we're going to see there's some argument that tells you, in order to prove this, you need to prove that A behaves well over sparse vectors. And as it turns out, that if you look, say, the whole set of sparse vectors is very complicated. But let's look at a specific case. You're in dimension P equals 10 to the 23. But you want to look at the vectors whose non-zero coordinates are perhaps the 10 first coordinates. So this subset is like R10, right? So it's a very easy set to understand. Except that the set of all sparse vectors with at most 10 non-zero coordinates is like several copies of R10. In the end, what we're going to do is something like this. We're going to use this sort of union bound idea again. It's saying that the set of say, you're in dimension P, and you want to look at sparse vectors with at most D non-zero coordinates, right? D being much smaller than P. This is like several copies of RD that are contained in RP. And there's a finite number of them. So if you can make everything work in each one of those subsets with high probability, then everything works very well over the whole space. Maybe I shouldn't be trying to give you an outline now because everything's sort of rough, but hopefully tomorrow things will make more sense. And in the end, we'll be able to prove a statement like this in a case that it's, which is this. Okay, let me just say what it is. So in our case, we're going to choose A, which is a random matrix. And it's a matrix like this. You multiply by 1 over square root of n, a matrix whose entries are all IID normals, standard normals. Right? And this is n times p. It's not symmetric, right? I mean, there's not even a square matrix, so it doesn't make so much sense to talk about symmetry here. The main point about this matrix is that you see, I mean, I already mentioned the fact that when you look at the square, you're actually looking at x in a product A transpose A x. So it turns out that when you consider this matrix here, you're going to get exactly the matrix sigma n that we had before, the distribution. So this is going to be 1 over n, a sum of I equals 1 n, xy, xi transpose, where these guys are normal with mean 0 and covariance matrix equal to the identity. So because we understand these matrices very well, we'll be able to prove things about this matrix here. And I mean, of course, this generalizes to the extent that if you take any matrix like this, right, it doesn't need to be IID with IID normal entries, but if you look at A transpose A, and you get some random covariance type matrix that you understand very well, then you can sort of replicate the argument we have here. So it's not specific to Gaussians, but even though it's sort of nicer with normal vectors. And actually, the sharpest known results, I mean, there's going to be a talk next Friday. Not this Friday, but I mean, during the workshop. There's going to be a talk about kind of phase transitions for this problem, trying to figure out exactly how, when you change n, p, and the sparsity of the vector, when is it the case that you can recover the beta min, or when is it the case that you cannot recover beta min? It turns out there's a phase transition for that in the Gaussian case, which is exactly this case we're going to study. So much more precise results can be found in this case. But in any way, I mean, if you want to get less sharp results of the kind of presenting here, then you can get them for many different distributions over matrices here. Well, that's all I have to say for today. So thank you very much, and see you all at 10 a.m. tomorrow.